and this is Philippa Marrack. Pippa moved to the LMB in about 1969, almost exactly the same time as I moved from LMB to biochemistry. So I remember the date. She did her PhD there with Alan Munro, and then she moved to the US immediately, and she's been there ever since. And it's from the US that she will speak to us today, hopefully, in a minute. Pippa is a fellow of the Royal Society, but also a member of the National Academy of Sciences. So Pippa, I hope you're there somewhere.
Okay, so to start off with, as Jean just said, but not exactly what she said, I got talked into becoming an immunologist by Alan Munro at some drunken cocktail party the summer after I got my undergraduate degree at Cambridge. And it turned out that Alan had planned to come to the LMB, I think about a year after I started my PhD. So the first year, we worked at the Department of Biochemistry in Tennis Court Road, and then we moved to the LMB. And then I got to learn whatever it was I had to learn. So Alan and I moved to the LMB, and I thought it was about 1968, but maybe I'm wrong. And we were given a bay, which is a small amount of lab. And there were 2 American postdocs in the same room as us, David Hirsch and Malcolm Gefter. Well, David Hirsch, if you know him, he's now in Boulder, sometimes in New York, is a very sweet guy and polite and friendly. And Malcolm Gefter absolutely hated the fact that there was a woman in the lab. And he spent a lot of time for the couple of years that we were in that lab trying to persuade me that I shouldn't be there. And actually what he taught me was not to be afraid of nasty, aggressive Americans. And so that's what I became, I think. And to tell you the truth, it's always been an advantage to be an English person in the States, because although I sound to you American, in the States I sound English. And every American knows that Margaret Thatcher and other women in the United Kingdom rule the roost. And so I get away with a whole lot of stuff. Anyway, I wanted to say a couple of things about what we do, but first of all, I wanted to say something about the way our careers are arranged. And listening to the 3 people who've spoken already, there's a message there, and there is, you better be careful what you start off studying, because the fact is you're going to become obsessed with it, and you're going to do the same thing for the rest of your life. So that's illustrated by a lot of different people's careers, including most of you in the room. But also, for example, a painter. So here's Mondrian. This is one of his early paintings in 1904, and it looks pretty non-Mondrian-like. But then in 1930, or at least probably in the 1920s, he started to paint these kinds of paintings. And what you can see is he continued along that line and made a whole lot of money and become very famous, just doing the same old thing in slightly more complicated ways. So here's a later painting. And here's, perhaps your favorite painting, which is even later. So his work becomes more and more complicated, but he's still doing the same thing. It's a bunch of lines and squares. So the same thing happened to me. I started off studying T cells and various kinds of lymphocytes with Alan. And most of these lymphocytes, the fact that there was more than one of them, had only just been discovered about 6 or 7 years previously by Jacques Miller and Bob Good. And we were interested in what the hell the T cells were up to. And one of the problems was that although these 2 different kinds of lymphocytes had been discovered, it wasn't understood how they, and was known that they recognize antigen in some way or another. But the idea was that, well, immunoglobulin molecules are really, really complicated. So T cells must use some version of antibodies. So here is a result that we published in Nature New Biology, 1972, which is one of the first indications, and it's complicated to understand the reasoning behind this paper. And when I reread it the other day, I found it incredibly complicated too, since that was weird to read one of one's own papers and not being able to understand it very well. But anyway, the idea is that if you prime a whole bunch of T cells so they recognize something, in this case, sheet red blood cells, which was everybody's favorite antigen at that time, you can then measure whether the T cells are specific for sheep red blood cells, i.e. do they have receptors on their surface that can bind that kind of blood cell? And the answer is these are pretty pathetic numbers by comparison what you would get out of the same kind of assay with B cells who are making antibodies. And in fact, the conclusion of this paper was that T cells don't bind free antigen, which was one of the first papers was not the first, but one of the first papers to show that T cells and B cells are going to use different methods of recognizing that the antigen they're supposed to be dealing with. Now, in this paper, the first author is myself. At that time, I was married to somebody else, not now. But actually, I'm ashamed to say that the order of the authors on this paper should have actually been this, because I don't remember that I actually did a single experiment that had anything to do with what was going on in it, which I've always been ashamed of ever since. And if Alan's listening, he can agree. Anyway, so there we are. T cells don't use antibody molecules, perhaps, to recognize antigen. And so that led to a race many years ago to find out what the T cell receptor actually was. Not everybody was in this race because there were a bunch of people who still thought it was antibodies, so they were up the wrong tree. Anyway, it turned out that if you look at these dates, it's the usual kind of thing, about simultaneously, not quite exactly simultaneously, unfortunately for us, because we were a couple of months late, as you can tell from these numbers here. The T cell receptor was actually discovered, and here are our various Western blots and IPs of what the receptor actually looks like. And in fact, it's two chains. Here it is, easily seen in humans and much more difficultly seen as two chains in mice running at this point. So this doesn't look like an immunoglobulin molecule, and in fact, it isn't. And here's the reason why. This is an antibody molecule from the Ian Wilson's lab binding flu hemagglutinin, and you can't see this very clearly here, but this is again in Hovech's crystallography at the LMB. The binding site of the antibody is directly in contact with the binding site of the flu hemagglutinin. So antibodies recognize their native antigen straight up. And then it took a lot of years and a lot of people's work, including our own, to persuade ourselves that the T cell receptor, here it is with its antigen binding loops in color, binding to an MHC molecule. This is the top half of an MHC molecule with a peptide down its groove. And the peptide, as you know, comes from an antigen. This is such an unexpected and incredibly ridiculous way to recognize antigen that there was no way that any artificial analysis of what's going on could have figured this out as a possibility. Anyway, this is the crystal structure of a T cell receptor binding its target, done in our lab by Xiaodong Dai, who's now an independent investigator elsewhere. So T cell receptors behave differently than antigen, and this is now 2008, which is many years later than Alan and my Ian McConnell's publication in 1972. So it was a lot of slog to get from there to here, and to get the community to agree that antibody was not a receptor on T cells. So for the rest of my life, I've continued to work on T cells, just like Mondrian continued to make little squares with black lines between them. And so right now in the lab, for example, a graduate student and myself are working on this issue. Most of the mice we work with are homozygous at their MHC alleles. For example, a black 6 mouse has MHC molecules, which we call B, little b. And if it's homozygous, it's a BB. And this is how many unique T cell receptors it has in the model that we're doing right now. And if it's an FF mouse, this is how many T cell receptors it has, different T cell receptors. And this again is MHCF. And then if we cross the two mice, so now you have the heterozygote. And what you would have thought is the mouse will have all the T cell receptors it could have got from its one parent and all the T cell receptors it could have got from its other parent. And it would have this many receptors, but actually it doesn't, it has a lot less. So the problem to figure out is, why is it evolutionarily advantaged? Because most of us are MHC heterozygotes. Presumably our mother and father were not related to each other necessarily. Why is it evolutionary advantageous to get rid of about half of your T cell receptors that you could have had if you were a mixture of your two parents. Like this mouse down at the bottom here, which is a tetraparental mouse, meaning that the two fertilized blastocysts were fused together to make a single mouse, and both MHCs are there. So the point is that MHC continues to, the major histocompatibility complex and how it deals with T cells continues to be a mystery with a lot of questions. And so my decision many years ago to follow Alan to the LMB and start being fascinated with T cells and continue to work on T cells all that time ever since, and how they recognize antigen may not have been a complete waste of time. So I'd like to finish up by saying a couple of things about the LMB. First of all, the cafeteria, the canteen, such a phenomenal place that's been mimicked in many different institutions where people have tried to encourage scientists to talk to each other rather than sit in their labs and not talk to anybody except a mouse or whatever it is. And the other thing that the LMB was fantastic about at that time, and probably still is, was the tremendous number of postdocs from all different parts of the world with their energy, vigor, and different points of view about how to treat a woman in the lab, which the women, if they can cope with it, become stronger because of. So it's training us in that way. So I'd like to end up with the words, the immortal words of Joni Mitchell. That's the way it is. It's paradise when you're there. And after you got left, you figure out that actually it was paradise and how wonderful it really was. So thank you very much for inviting me. And I think it's about to snow right here.
Oh, yes, Joan.
So Pippa, do you think that there's any difference to your last question as to how to treat a woman in the lab in the US versus the UK?
Officially, no. But in practice, there's two aspects to being a woman, and I think this probably applies in the UK as well. That on the whole, at least for some years, organizers of meetings, when there actually were meetings, and so on, are very anxious to satisfy their genetic components of their departments. So they're looking for women, or they're looking for women to give talks, because they can't have a program that's full of men. That will induce a tremendous amount of acrimony. So from time to time, it's been an advantage to be a woman. And those of you who work in the UK can tell me if that's true in the UK as well, that a woman who's senior and been around a long time does get a step up from time to time in various kinds of public things. That's not to say that in the background, they aren't coping with other issues. When I talk to junior scientists about this kind of thing, I always try to say, well, you have to pretend that you're actually from Mars, a green Martian, and that you don't have to obey any of the rules that all the other people that live in your society have to obey, because you come from somewhere else and they haven't a clue what rules your tradition has trained you to follow. So you can just do whatever you like, because the others are not going to be able to criticize you. They think you're Margaret Thatcher and you just get on with it. I don't know. You can tell me if that applies in the UK.
I'm not sure it does, but anybody else? No. Okay, I think you've got off lightly there, Pippa. The issue,